So I want to begin with a come together moment. So, no touching. Laboratories, are a very important member of your sampling team. And, no one wants to resample. Sometimes it's, mistakes are made, and it's unavoidable, but you really don't want to have to resample due to a communication error. So all of the speakers today have talked about DQOs, and I couldn't agree more. It's very, very important from our perspective, how you plan out your project, and of course include the laboratory in that. And for the purposes of this talk, it becomes even more important because that's really how you evaluate your data as far as whether it's usable or not. You want to compare it to what you said you were going to use it for in the first place, and that's the first step of doing data usability. So sometimes it's the simple stuff that can derail a project. So you always want to make sure you have the logistics right, have that conversation with the laboratory, in advance. And as far as hold times go, always recognize your samples have a shelf life. Your data also has a shelf life, and I'll bring that up at the end of the talk. But as far as hold times go, if you're out on a site sampling over a week's time, you should ideally be delivering your samples or having them picked up every day you're sampling, so that you maximize that available hold time and makes chain of custody less complicated and all of that. The other important thing is making sure that whatever it is you're planning, as far as from the laboratory or the analytical point of view, is compliant with whoever has regulatory oversight over your project. Sometimes there's multiple regulators involved, like an EPA in the state or DOD in the state, and so you have multiple regulators involved. It becomes a lot more complicated. Things like with EPA, if it's a TSCA program and you're sampling for PCBs, they have very specific requirements. Those of you who have worked in Region 1 would know, and you want to make sure that you have that discussion with the lab as far as making sure that it's compliant with TSCA. Certifications are also somewhat complicated in that every state does it a little differently. And some states will certify by the analytical method. Other states will certify by the individual analytes. So it can be difficult to, just make sure that the laboratory is indeed certified under the state requirement or DOD that you need. You also want to make sure you talk to the laboratory about just what it is that's specific about your project that the lab needs to know about in order to meet your expectations. And one of the most important things is what list of target compounds are you looking for. Labs have standard lists, but you want to make sure that that list will work for your project. Sometimes there's a compound that you need that maybe it's an unusual one or just one that's not on the lab's list. You want to have that discussion, and you want to make sure that sometimes when there are those odd compounds, there may be a special method or even method R&D that's going to have to be done. Having that discussion early So perhaps the most important thing, and the thing that maybe causes the most consternation with sampling programs, is reporting limits. You definitely want to make sure that you discuss with the laboratory what regulatory criteria you need to meet. Make sure that the lab's detection limits are going to satisfy that criteria. And there are a lot of sometimes there are problem compounds that just won't meet those limits, and you have to have that an honest discussion with the lab as far as what's the best they can do for a certain compound. There are other things like some usual suspects that come up. EPH in Massachusetts, it's a GCFID run. You can report the priority pollutant PAHs this way in an aqueous sample. However, if you do need to meet the low detection limits like Massachusetts GW1, that analysis won't achieve that. You have to ask them to do the PAHs separately by mass spec. Same thing with EDB, dioxane in an aqueous sample. These are 8260, the VOC method targets. And if they're not contaminants of concern, you just want to do it by 8260, that's fine. However, recognize that if you need to meet those low limits, those need to be done by different methodologies than 8260. Another, like one of my personal favorites, vinyl chloride, if there's, request to hit a reporting limit of, half a part per billion at a dry cleaner site with, multiple ppm of PCE, very, very difficult to do that. Probably impossible to do that. If that's really your expectation, again, you really want to have that discussion with the lab to try to work that out in advance. Sometimes samples are really wet, soils and sediments. Dry weight correction plays havoc with reporting limits, or sometimes there's other reasons for dilutions with gross contamination or other things. So detection limits aren't always a given, I guess is what I'm trying to say. And because they're so important, I just wanted to give you a little background, and we're going to use water because the math is a lot easier to deal with. So say if you started with a liter sample and you extract that with say 300 mils of solvent. So all the trace organic constituents in the water are now in that solvent. We're going to concentrate the solvent down to a mil. That's 1,000 to 1 concentration. So if your instrument can only see a part per million, when we multiply it times 1,000, now we can see a part per billion. So that's really where all that sensitivity comes from. It's not the the fancy instrument on the bench. It's more of the prep work. However, things can go wrong in this process. If you have a sample like this, and you concentrate it down, 1 mil is the bottom thimble there, actually half of that. This is not going to get anywhere near there. There's so much organic material, it's not going to concentrate down. We'll be lucky if we get to 10. So right off the bat, the detection limit here is not 1 part per billion, but 10, and it's probably going to be higher because looking at that matrix is probably going to have to be diluted even more. So that's what happens sometimes. So your basic lab report, summary report, is going to have a cover page. If it's one of those state programs, it's going to have a questionnaire certification page with it. It's also going to have, or should have, a case narrative. And on the results pages, not only do you have your sample data, but you have sample-specific QC data, like the data was analyzed, so you can check the whole time surrogate recoveries if it's trace organics analysis, stuff like that. Labs are going to analyze your samples in a batch. So we group together typically 20 samples, then we add quality control samples to them and run them through. That data is all reported in its own separate section. Now there's some other things that you could get from the lab as well. Many labs have online data summaries, essentially spreadsheets and tables and stuff that your data is going to be available in. If you're doing a data validation where you really want to review everything, and I mean everything, I call this the banker's box version. You're going to get 2,000 pages of raw data and computer printouts and stuff like that. But that's what you need if you really wanted to do a complete validation. Then also, lots of people have their own specific electronic formats, and you can get those EDDs from the lab. So what is the big deal about usability? Well, it's about managing uncertainty and, essentially interpreting that in the risk of making a wrong decision that's not going to be protective of human health or the environment. And it kind of all focuses around your risk tolerance, and we'll talk about that a lot, actually. But you don't really treat your data the same way. I've got two really extreme examples. A cleanup verification sample versus the initial site screening. Presence or absence, that kind of thing. That cleanup, that verification sample after your remediation program, and you want to demonstrate to the regulators that the site's clean, meets all the criteria, that data is not going to have a really big risk tolerance on it. You want that to be really tight. On the other hand, just going out presence or absence, you have a lot. You could have a lot of sway in that data, and probably it will still serve that purpose. So that's kind of like how you treat it in your mind. So EPA has a couple of different ways that they approach uncertainty. The CERCLA program, they set up a long time ago, the Contractor Lab program. This is a very prescriptive program where all of the analytical methods are specified right down to every last detail. And then what is reported back to you is also explicitly laid out. So you get all that data, the person getting the data, the data user, how the analysis was conducted exactly, and then you have all of the backup documentation to review and make sure that everything is correct. So that's one way of getting data of known quality. RCRA office has a little bit of a different approach. They have that SW846 manual. It's really a guidance manual where they have all the methods are listed in there, 8260, 8270, and so forth. However, there's a lot of you should do this and you should do that rather than you shall do. And where a lot of that specifics comes from is in the QAP. So when you set up a project, kind of under this approach, you have the QAP. That's where you specify the accuracy and precision and detection limits, for example. This DQO document first came out in 1984. It's been revised, I believe, at least twice since. Has a lot of good information. A lot of the speakers during the day discuss this topic. So the states, Connecticut, Massachusetts, and New Jersey, all developed a different, somewhat of a hybrid approach, actually, to these two examples from EPA as far as how to generate data of known quality. And essentially what they all are is an overlay that has all of those specifics, the recommendations, the requirements, the actual criteria that's overlaying on top of an SW846 method. And there are several, they're not available for every method, but they're available for most of the usual suspects that you would use in site characterization and remediation. And they are a very good tool. We'll talk a little bit about them. So as far as data quality goes, we're really talking about qualitative and quantitative uncertainty. So using a fixed lab, unless you're dealing with TICs, tentatively identified compounds, qualitative uncertainty isn't an issue. But quantitative uncertainty certainly is. All measurements have some degree of uncertainty. So in order to evaluate that, you'd use the PARCCS parameters. This is a very old acronym, but it stands for precision, accuracy, representativeness, completeness, comparability, and sensitivity. So from fixed laboratory data point of view, we're really only going to talk about these three. However, most of the talks earlier today, all of them really were really talking about representativeness, a lot of good representative stuff. And I know from what I've read and what I've heard, when you think of the total uncertainty associated with a program, it's at least 80% representativeness related. So it's just food for thought. So we have the one obligatory QA/QC slide. Most people think of that as interchangeable QA/QC, but they're really quite different. So QC, I like to think, has two major components to it. The first is like the infrastructure. Does the lab have everything in place? The chemists are properly trained, the instrumentation is maintained, and it's the right instruments. Everything is in place, conducive for them to do a good job. Second is this continuing monitoring focus, where as these samples are going through the lab, that batch QC is being monitored and control charts are generated to make sure that every analysis is still within control, and you can track trends this way. But the other purpose for that data, and this is what makes sense for you folks, is so that there's all that project-specific data quality indicators. That's what that acronym stands for. The blanks and spikes and duplicates that get run with your particular samples. That is reported to you in your report, and you're able to then do your data usability assessment to see how things look. That's what you use. So all that QC is expensive and time consuming. So left to their own devices, human nature, maybe you would get a little bit of a short circuit there. So the QA, that's their role, is to really just to make sure that the QC is being done, and there's a number of ways that's performed. So these things in red, that's what's known as a quality system. So when a lab is audited or when a lab is certified by a particular agency, that's when they come into the lab, that's what they're looking at. They're really looking at the lab's quality system. So that means, again, they have everything they need to do the correct job, but it doesn't mean that everything that's coming out of the lab is of known quality, and specifically, what's in your specific report. So you want to do some analytical work, and you want to end up with data that's usable for what you said you were going to use it for. But how do you get there is the question. So what's most important is, again, how the samples are analyzed and making sure that you've got data of known quality. So if you start with that, then you can do this data usability assessment after that. So we'll talk a little bit more about that. So known quality, known PARCCS. So we know the accuracy, we know the precision. So sometimes people think, known quality automatically means high quality. Well, quality is really a relative term. Going back to my first example there, if I had a handheld PID and I was just trying to find hotspots or for VOCs and maybe presence or absence, that data might be high quality for that screening purpose, but I certainly wouldn't want to close out a site with it. So a couple of different ways to get to known quality. All things considered, maybe the easiest way is to use one of these state programs. Massachusetts Compendium, Connecticut Reasonable Confidence, and New Jersey's Data of Known Quality. They're all very, very similar, and they're designed to generate data of known quality if everything goes well in the laboratory. And the acronyms they use for known quality, different acronyms, but they all kind of mean the same thing. So the other way is get data, get a full data deliverables package and have a very comprehensive QAP that you've given to the lab outlining what it is you want them to do and how you want them to do it. And then you get data validation performed on it, and they'll go through and they'll mark up all the non-conformances, so you know where you stand with that data set. So the third way, a lot of times you could end up in this boat where you don't have, you didn't use one of those state programs, and you didn't do the Banker's Box version of data reports. So you're trying to make do with what you have, and in a lot of cases, depending on what was done and how you did it, you can get a lot of the way there. You can still certainly look at blanks and duplicates and all that kind of stuff, though it's not the complete package of data usability. So just one couple of slides on those programs. So as I mentioned, you know, it essentially tightens up the SW846 method, and there's a specified report content. So the lab is going to report to you all of the information that you need to be able to do a data usability assessment. And lastly, there's that cover page. It's a questionnaire where they ask questions are directed to the lab as far as individual things that may or may not have gone according to plan during the analysis. And it's a good summary for you. It's just an example page, and there's several pages per method of the type of information that's specified in these methods. So that being said, you have data of known quality. Now, how do you do the usability? Well, one way easy to comprehend it is essentially break it into two parts: the data quality assessment and the usability evaluation. And so in the assessment part, it's an academic exercise. You go through the report and you identify all of the non-conformances. The usability evaluation, once you have that, now you compare, you know, the flaws in the data to what you said you were going to use the data for, and that's where that risk tolerance thing comes into play, among other things. And now you make the evaluation whether or not you can use such and such a result for your purpose or not. So you know, to start the assessment, if you were using one of these state programs, you need yeses to all of these questions except this question H. The other two states have different designation. I'm just using Massachusetts here. But you need yeses to the A through F section of this questionnaire. And if you get yeses, that means you've got data of known quality. The H question here, were all QC performance standards met? Well, you can have data of known quality, but the surrogate could be out, or there could be a hit in the blank, or things like that. That's still known quality. There's a flaw in the data, and you know it, but but it's telling you that. So that's an important question. If you get a yes to that question, though, you kind of like you hit the lottery because it's unusual. These methods are very, very rigorous and hard to get, you know, hit every single requirement on every sample. But if you do, you don't really have to do a usability assessment because it means it's usable for all purposes, except you still want to look at the detection limits because that's always going to be in play. And as I said, unfortunately, it usually doesn't end up that way. There's usually something to look at, and you just want to document them. So you know, to start off, really where you want to really spend a lot of quality time is with that narrative, and the laboratory should be summarizing for you what the issues are. And it should be in the form of like an exception report. They're not telling you everything that went right. It's here are the things that you should be aware of, data user. And it's a good place to start. That batch QC section in the back of the report, that's where all of that data that covers all of the QC that was run with your samples, that's in there as well. And you know, the data pages themselves have the surrogate recoveries and other sample specific things on it. And you know, what are you looking for in all of this? Well, again, anything that can point to accuracy, precision, and sensitivity info. So you can think of, you know, in your report, there's potentially 3 layers of QC information. So the first being, you know, if you've submitted field QC, that's one level, and that encompasses the whole sampling data collection activity from the field all the way to the lab. The next one, you know, starts at the lab. We do the batch QC. Blanks and LCS, LCSD, that's laboratory control sample and duplicate. Those you can consider being blank spikes, and you should always make sure when you get a lab report or you're setting something up with a lab that their LCS covers all of the target analytes. that you're looking for. Sometimes you'll see a subset, and that's great for the subset, but it doesn't tell you anything about the other compounds. And then sample specific, for trace organics, we're adding surrogates to them, and that's per sample. And also blanks, hold times and stuff is also another indication of bias as well. So looking at accuracy, it is really, bias, and several speakers talked about bias from a laboratory point of view, fixed lab. We're talking bias, and we're looking at blanks and spikes as indicators. For any type of spike, the metric is % recovery, and you can think of that as, say we spike in 100 parts per billion of something and we get 80 parts per billion back, that's 80% recovery. And then all of our performance windows are all worked for accuracy are based on % recovery. It's either in or out. And the other thing to remember is % recovery can be positive or negative. We can get 120% recovery. Instead of a suppression, there's some kind of enhancement. So the data quality indicators, again, the LCS, LCSD, you get individual accuracy data for every compound, which is great. If you do the LCSD, you can also measure precision that way as well. Any type of blank is essentially a positive bias indicator. And then again, the surrogate spikes, whereas the LCS are the actual target analytes in a blank matrix, surrogates are compounds that are chemically similar to the compounds of interest spiked into each individual sample. So surrogates are a nice sample-specific indicator of any % recovery issues, whereas batch QC is supposed to reflect all of the samples run in that batch. So again, the hold times, usually a false negative bias there. Field QC, sometimes you're going to ask for a matrix spike, which is the same spiking solution as an LCS. However, we spike it to your individual sample that you would tell us. And typically, because there's a lot of QC and a lot of accuracy information for organic analysis, typically a data validator or usability assessor like yourself might want to just focus on that specific sample for the matrix spike. However, for inorganics like metals, there's not as much accuracy indicators. So typically, they will apply the matrix spike over the whole batch for metals, for example. And then, yeah, again, all of these types of blanks, all false positive indicators. So how you see, well, what you'll see in your report is you'll see a % recovery for whatever analysis that is. And then there's a window, whatever the acceptance window is. And, in this first case, it's below the window. There's some kind of suppression, indicates a negative bias. The reverse for the second example. One thing, you don't want to do the math here. You don't want to correct your result by this % recovery. It's generally not a good idea. And another important thing is make sure you understand what the recovery window, what the laboratory is reporting. In some cases, it might be that state program that they're working under with that acceptance criteria, or is it the lab-derived criteria, or is it you may have a project-specific criteria you ask to be reported, if that can be done. So you want to make sure you understand what the lab is using as the criteria benchmark. So let's look at that again, though. So in this case, we've got a result of 50. We've got a pronounced low bias here, very pronounced. And we have an action level of 55. So this is the scenario here that you really want to be on the lookout for, because what this indicates is I've got 50, I've got pronounced low bias, but I'm right up against the action level. This is a cause for concern, because maybe if things were different and you didn't have that 22% recovery, maybe that 50 is greater than 55. So this is the scenario to be looking for the big red flag is stuff like this. So you always want to look for that. Same result, still low bias, not as bad, but this time the action level's 1. So I've got a suppression here, but I'm already 50 times over the limit. So in this case, there's absolutely no data usability impact at all. Whereas in the first case, there's a significant data usability impact. So same result, same low bias, but big difference. So the thought process that I go through is, what's the direction of the bias? Where's my result in relation to the action level? And then the last one is your risk tolerance. How much fluff in the result can you stand to be able to use the result? Again, I go back to the first example where cleanup verification versus screening. You might interpret these differently. So precision is different. Precision is variability. How reproducible? And the metric there is we're using any and all type of replicates. And for duplicate analysis, we evaluate it by RPD, absolute value of the range over the mean. And again, all of our acceptance criteria for these methods for precision, it's specified as percent RPD. And so, LCS, LCSD is a great way to get precision information. You may ask the lab to do a batch duplicate on one of your samples. That's another way. Certainly field splits, field dupes, and MSD, all of these you can do, you can calculate precision on. RPD again? Relative percent difference. And for any of these field QC samples, you always want to submit them blind. Don't submit a sample MW1 and MW1 dupe. These are supposed to be totally objective, right? And you'll have the chemist on the bench, these are duplicates. They look like, you don't want any of that. You just want it, MW1, MW77, and but on the other hand, so we don't know it's a QC or a dupe. We're not going to calculate the RPD. So when you get the data back, make sure you do that. You paid for the sample, you might as well get the info. So example of how this works, it's the criteria is an upper limit. So if the RPD on your analysis is less than the upper limit, you have acceptable precision. If it's greater than that, you have increased variability, or Connecticut calls it indeterminate bias. Don't know what direction it's going in. So just a visual here, what we've been talking about. So we've got a result of 9. If we were right at the limit of 25% RPD, that's about what the spread would be. That's your error bar. If we had not as good precision, there's a greater error bar. And let's say there was some bias there, so then the whole error bar moves in one direction or the other. So this is conceptually kind of what I've been talking about. So now we'll change gears and talk about detection limits. This is really old school here. Back in the day, we'd do a calibration curve, and we'd actually put it on graph paper. It was a long time ago, so this is a calibration curve, and it's nice and linear, which is great. They're not always that way, and there's 5 calibration points. One of the things that on those state programs, like all of the stuff that they put into those overlays, one of the things is how many calibration points. So they will specify 5 calibration points, and obviously the more calibration points you have, the better the quantitation is going to be. So that's a good question to ask a laboratory if you're not following one of those state programs. And so the way this works conceptually, again, is we get a signal, we get a response, we drive it over to the line, go down, and that's the concentration, slope factor, obviously. So that's how that works. And another great thing with those state programs is they set the reporting limit can be no lower than the lowest calibration standard. So there's some really strict requirements as to what you can use for calibration points. That data point has to meet a lot of different criteria in order to be used. So you're absolutely certain at 5, in this case, 5 ppb, that or not more than 5 micrograms per mil. Wow, that you have a very you have a very solid reporting limit. There's no estimation. But there's also something called an MDL, and RLs and MDLs. There's a lot of different terminology out there now about detection limits and reporting limits, but I'll just use these as an example. The MDL represents the theoretical lowest point that the laboratory can see, and in between those two, there's a zone, there's a gray area. So you may have gotten data back that is reported less than the reporting limit, but with a J flag. That's what that means. It means we're certain that there's benzene in the sample. We're just not exactly sure on the quantitation because it's below our RL. So that's where those J flags come from. Again, you always want to make sure that you tell the lab what the criteria is you're doing. And again, in a situation like dioxane or something like that, the lab needs to know that that's the limit you need, and then they will suggest to you some alternative methods. Again, sometimes, like the example I showed you, there could be dilutions that are required, and reporting limits will be impacted. So you really want to focus on why you got to know, or why there's some non-conformance, and then isolate that. If it's full priority pollutant scan, you just got VOAs that had an issue, you can ignore everything else. Maybe it was just one compound in the VOA list, ignore everything else. That's all you have to look at. Again, you still have to look at detection limits. You want to evaluate essentially how relevant is it. So a lot of times there's a lot of problem compounds, oxygenates and what have you, that may or may not be contaminants of concern, but typically you always have some data usability thing. If that's the case, you could probably minimize it. On the other hand, if it's contaminant of concern, you can't minimize it. What location? Is it that one down gradient well? That's a pretty important sample. You want to make sure that that data is tight. Or is it, I've got 20 or so, I'm doing exposure point concentration, 19 of the samples are perfect, this one had a flaw. That will also, taint your how you look at things. And again, factor it all into the risk tolerance of what it is you're going to use the data for. There can be multiple lines of evidence here. Sometimes the blanks, the spikes, whatever, all point in the same direction. That's great, makes things a lot easier. But a lot of times they don't. And so you have to kind of tease that out. And you also have other info like historical data, field screening, some trade-offs. How bad is it? Is it really bad, or is it just out? EPH for Massachusetts, I believe the criteria, the low cut criteria is 40%. If you get 41%, it's acceptable. And that's just a reflection of how difficult it is to do EPH. So, again, if you get 38%, okay, it's out of criteria, you have to note it, but really how much different is it? You can justify that. So again, that's what it comes down to, can you justify it? And in most cases, you can justify it for certain uses. So just to wrap it up, you have the DQA part, identify the non-conformances, and then evaluate them. So you are generating a lot of data. So you want to summarize it in some kind of table. This is an example of Alpha's data usability table, but others have others. Just want to get it in some kind of spreadsheet, so then you all use the same, you're using qualified data to make your decisions. And then lastly, your data has a shelf life. When you get a report back, you really should be all excited and look at it right away to make sure that everything is there's no big red flags in the data set, right? So, because if there is, or if you have some like giant question mark on a given result, you can call the lab, and maybe it's still in hold time and they're gonna run it for you, or they can reevaluate it, or they can do stuff. If you wait till your report's due 6 months later, they're not gonna have the sample. They're certainly not gonna be able to rerun it for you, and you got less options. And that's all I have for you. Thank you.
Questions? Oh, wait, I got one. Percent recovery. So is that just totally something that happens at the lab? And is there a point where you say, oh, something went wrong and that percent recovery is so low, we should do this again ourselves before I give the client the data? Or
absolutely. You know, most like those state programs and other yes, those state programs, EPA, data usability guidance, they all have that criteria, those windows, acceptance criteria. And depending on where you are, there's all kinds of corrective actions that are mandated. And sometimes it's you re-extract the sample, you reanalyze the sample, just in other words, you do it again. And sometimes they're reproducible because of the sample itself and you can't do anything else, but at least you've proven that it's a matrix effect and not just something that went a bad day in the lab.
Okay, anything else? Oh, another one.
Well, I have a question. If you are requesting a lab for a specific subset of analyses, like ticks, for example, like BTEX, you're asking for BTEX, but then you identify that there might be some fluoride solvents. Is there an obligation for the laboratories to report that to the person running analysis?
Okay, repeat the question.
So I believe the question, Cole, was so you're doing BTEX and you have ticks and there's potentially chlorinated solvents in there. Is the laboratory obligated to tell you that? Well, that's a very long answer, so I won't go into the length. But in quickly, the original, like for example, VPH method by GC, unless it was like really obvious because you only got a gas chromatograph, sometimes it's a gray area as far as whether or not these peaks are hydrocarbons or not. So the rules of engagement in that regard are that if you ask us to tell us, we will. However, that's why that new mass spec method is now out, and with a mass spectrometer, we know exactly what is there in the sample, and you can ask us to not include those in the sample, and a lot of times it will make a big difference in those ranges as far as your concentration goes. The lab will say in the narrative, however, that certain peaks were not concluded.
Okay, anything else on the labs? Okay, well, thanks again, Jim.